Now, I want to warn you that some collisions don't look like collisions. I told you that all collisions are momentum problems, and in all collisions, momentum is conserved, even if C4 is involved. C4 is an explosive. Well, here's an explosion that is a collision. Okay, we've got an astronaut in deep outer space. He pushes a button. The propulsion unit strapped on his back ejects some gas with a velocity of 32 meters per second to the right. The astronaut recoils with a velocity of 0.3 meter per second to the left. After the gas is ejected, the mass of the astronaut is 160 kilograms. What's the mass of the ejected gas? So here's what that looks like. He's just floating in deep outer space. Just da-da-da-da-da-da. I gotta get home. So he points himself in the right direction, pushes the button, and whoosh, there's a Wall-E sort of a thing. Okay? Now, what do you think? Conservation of energy or conservation of momentum?
Momentum.
Yeah, momentum. Let's look at energy. I mean, if he's far away from any planets, that's a kind of a big stretch, but if he's far away from any planets, there's no gravitational energy, there's no springs. When he's just sitting there, there's no kinetic energy, and then suddenly he's got kinetic energy, the gas has kinetic energy. Does this leftward kinetic energy cancel the rightward kinetic energy? No or heck no? Heck no, it's just energy. Kinetic energy is always positive. He's got some, the gas has got some, there's some. There was none. The type of energy we've got formulas for is not conserved in this problem. Okay? That Varick energy equation is not going to help us. What's happening here is chemical potential energy that we don't have a formula for is being transformed into kinetic energy, but we can't deal with it that way. But we can look at momentum. Initially, he has no momentum, he's not moving. After the button is pushed, he's got momentum to the left, the gas has momentum to the right. If momentum's conserved, I can set the initial momentum equal to the final, and that's what it looks like. Now it's math. I solve for m and I get 1.5 kilograms. Okay? I told you we were going to do rocket science, didn't I? Rocket science. Okay. Now I've got a little market survey. Momentum is conserved during a collision. What does this mean? A, total momentum for the system adds up to 0 before and after the collision. Or B, total momentum for the system stays the same before and after the collision. With your clicker, would you please tell me what you think that means? Okay? Okay, B is the correct answer. These people are confused and this person's, well, always with us. Okay. Now, the reason those people are confused is that we've had a lot of examples where momentum happened by coincidence or design to be 0 before and after. But that's not what it means to conserve something. To conserve something is whatever you got, you keep gotten it. Okay? To be numerically correct.